I'm Steve Kinney, Director of Technical Sales and Support for JAI. I'm also AIA Camera Link Committee Chairman. I'm an electrical engineer who began my career in the United States Air Force as an avionic inertial navigation specialist. I've done several years beginning in 1990, coming back to the Silicon Valley in product design and development, and began my career in machine vision with a camera company in 1997. My years in the Air Force, along with product development, give me a broad perspective on all types of customer situations and equipment, whether it be pneumatic or electrical, and give me a broad base of experience for helping customers and applications. Today I'll be talking to you about the fundamentals of camera and image sensor technology, teaching the basic course for the AIA CVP certification. I'm going to speak in 4 segments today, beginning with light basics and CCD CMOS imager fundamentals, continuing to digital camera principles, interfaces, and finally camera types and when to use them. We're going to begin with the light basics today. Light is a piece of the electromagnetic spectrum, which includes everything from long-wave radio through your TV, microwaves, finally moving into the light, both infrared, visible, and ultraviolet, and continuing on through gamma rays and X-rays. I always point this out because a lot of students don't recognize that light is in fact an electromagnetic wave and the same as radio. And one of the key points to be made here is light is actually a very narrow band. When we look at the total spectrum of RF energy here, light is a very narrow band, and when we talk about applications, we actually talk about dividing the light up into finer detail from near infrared to the visible section to the ultraviolet, and we're actually slicing a narrow band into even narrower pieces to work on our applications here. We're primarily interested in wavelengths of light from 200 to 1100 nanometers, with the bulk of that being visible light from 400 to 750 nanometers. This is the energy that your eyes see as visible light and that most cameras focus on for imaging. But for machine vision, we also see applications in the near UV from 200 to 400 nanometers. And sometimes near infrared light is also used from 750 to 1000 or 1100 nanometers. Light is represented as both a particle and an electromagnetic wave. A light particle is called a photon. Photons have some energy, and the amount of energy in the photon determines the wavelength. So since the speed of light is a constant, if there's more energy in the light, it vibrates faster and it becomes a blue wavelength, whereas if it has lower energy in it, it will vibrate slower and be a red wavelength. The wavelength corresponds to a color as I just described, and the intensity of light is represented by the number of photons being emitted by a surface, and the color light is the wavelength of those photons. So all sensors in the cameras then work on what is called photoelectric effect. Photons are converted to electrons. Light hitting a silicon surface will dislodge the electron. When the light hits, it peels it out of a valence orbit, and the electron is dislodged and it's held on the imager in some fashion and counted in some fashion, which we'll discuss shortly. The number of electrons then released depend on the intensity and the wavelength of light. For sensors, we often see the quantum efficiency represented on the data sheets. Quantum efficiency is the ratio of light that the sensor converts into a charge. So 60% quantum efficiency means that for every 10 photons hitting a pixel surface, that 6 are converted into charge. QE is sensor specific. Camera design does not affect the QE curve. So these curves that you see here are given to us by the sensor manufacturers that we use in the cameras. And while we want to do good things electronically in the camera to maintain the best from that sensor, nothing we do in the camera can change the quantum efficiency or the response of that sensor to light. QE is also given in absolute or relative terms. The sensors that I've shown here, you'll notice they say absolute quantum efficiency. This means they are absolute in that effect I just talked about. So if you have 60% QE, then that means 6 out of every 10 photons are hitting the surface and being registered on the sensor. Some sensor manufacturers give quantum efficiency in what is called relative terms. Relative quantum efficiency simply means that the manufacturer takes the peak of the curve, whatever that peak may be, and they normalize it to 100%. So in these curves, this sensor is slightly over 50%, so this manufacturer would take a multiple of just under 2, multiply this peak till it came to 100%, and then redraw the curve multiplied by that factor. Relative QE is good for that sensor only, so that you can tell as I change the wavelength of light coming in, or if I were using monochromatic sources, how much response I would get from that sensor only. However, because it's been normalized by a factor that's unknown to the user, you can never use relative quantum efficiency for comparing one sensor to another, even if they're from that same manufacturer. The full well capacity of the sensor, or of the pixel, is the number of electrons that register in a signal in a pixel. Larger pixels have a higher well capacity, which also tends to lead to higher sensitivity, better signal and noise, and increased dynamic range. So these are typical, these are not absolute, but if we look around at sensors that we find in the industry, very small pixel sensors have full well capacities around 4,000 electrons. A more medium-sized pixel will then have well capacities more like 10,000 electrons, and larger pixels can hold 50,000 or more electrons. So now we're going to talk about applying some of these basics and talk specifically about CCD and CMOS sensors, what's going on with them, how they're converting the light to the charge, and what they can do for us in imaging. The main difference between CCD and CMOS sensors is how they transfer charge out of the pixel and read it out of the camera into the machine vision system. CCDs read charge and clock them off the face. CMOS imagers collect charge in the pixel and then read out circuitry in the pixel, lets it read it out of the camera. When we think of a CCD sensor, we can think of it as a bucket brigade. We can imagine a CCD pixel is a bucket collecting light, much as a bucket out in the open would collect rainwater when it rains. And once that light is collected, a CCD type sensor then shifts that light on the surface of the sensor and out of the sensor into the camera body. So CCD stands for charge coupled device. That's important because charge coupled device means that CCD imagers are current driven devices. The charge is physically collected as a number of electrons, and those electrons are collected in pixels and moved on the sensor surface. The charge is physically shifted around by various voltage barriers, and as those barriers are dropped, the charge can be moved from pixels into shift registers and then clocked out of the camera. So when the camera is beginning to read out a frame, it drops all the charge vertically into a horizontal shift register at the bottom of the imager, reads out that horizontal shift register as a line in the image, and then creates another vertical shift, dropping all the charges down one more into the horizontal shift register, reading those out, and so forth till the last line has made it to the horizontal shift register and is clocked out. Again, much like the bucket brigade on the previous slide, just first in, first out type of situation. The CCD output then is an analog pulse where the charge is proportional to the light intensity. So when you read out the sensor, a CCD is a quasi-analog device. The blip produced is actually an analog blip, even though it's being controlled and read out with digital pulses to control the timing and the readout. CCDs by nature are quasi-analog. Microlenses increase the photon collection of the area of the pixel and focus the photons into the photosensitive area of the pixel. So we'll talk about this even more in CMOS, but both CCD and CMOS imagers, you have a pixel area, but the pixel area has to include other structures to read that charge out of the pixel and control the pixel shutter time and readout and all the other things to get the information from the pixel into the camera. That means by definition that the whole pixel cannot be photosensitive to electrons. It means there's only a small area, usually called a photodiode, that is sensitive to the photons coming in, and the rest of the structure is then not photosensitive. So to increase this photosensitive area and to increase the quantum efficiency overall per the curves I showed, CCDs tend to use a microlens over the surface. The microlens can be thought of as just a big magnifying glass over the pixel area. Essentially, the manufacturers are able to create this over every pixel, and all that's happening is the light that's coming in at oblique angles that would not normally strike the photosensitive area would come in and maybe strike a shift register or something, are bent through the magnifying glass to be focused down into the pixel area. Almost all modern CCDs use microlenses. There's very few exceptions. There are some application exceptions, especially in the UV, where the microlens is undesirable. But as a starting place, almost all visible CCDs use microlenses today. The pro is they effectively increase the quantum efficiency of the pixel. The con is that they create an angular sensitivity to the incident light ray. So even though the light can come in at a steep angle and be bent into the photosensitive area, it's not perfect, and we can see a roll-off in the response of the pixel to light with the angle of incidence of the light to the pixel itself. So what you see in this diagram is that if this is a lens and this is a CCD surface here, rays coming on axis through the center lens and being focused on the pixel are then hitting the pixel essentially on axis and collinear, and the microlens can very effectively bend all the rays into the center of the photosensitive area on the pixel. However, if we look at a peripheral ray coming in at a steep angle, then we'll see that the pixel in this area of the sensor has to bend all the rays coming in, and that while it can do this efficiently, that some of the steepest rays coming at the steep angle, even through the microlens, will be bent in a way that it can't quite make that center photosensitive area. This means that the quantum efficiency is then affected by the angular incidence of the ray itself. So we can see this is an actual chart for a Kodak KAI 340 CCD. And we'll see, especially in the vertical, that the CCD has a very high efficiency with angle, but as the angle increases beyond about 10 degrees, that the efficiency begins to fall off. But we'll also notice they give this to us in terms of a vertical efficiency, and that horizontally there is a different efficiency, and that in fact this particular imager is more sensitive to horizontal shading across the horizontal of its surface. And this is due to the fact that the photosensitive area is not always in the center of the pixel, and the fact that it may not be square. In fact, most cases it is rectangle, and thus you see that there is a larger vertical collection area than a horizontal collection area, and that when we talk about these microlens effects, it affects these differently. So applications that are very dependent on uniformity and shading need to pay attention to this, because the sensor itself will have a uniformity response, but assuming all the rays are on axis, and that if we add a lens to the system and it brings rays in out of off axis, that in fact will affect the uniformity. And in general, the wider the angle of field of view of the lens, the steeper those rays on the peripheral, and the more vertical and horizontal shading we are going to see. Microlenses increase the pixel effective area. This is often called fill factor. And they produce a high fill factor. Horizontal lines are shifted down the surface of the sensor, as we described. Pixels are read out from a horizontal shift register through a common circuit, including an amplifier to give us a pixel readout. So the main advantages of CCDs are sensitivity. The main disadvantage is then speed. And this comes back to what I was saying about the charge being rolled on the surface of the device. Because a CCD is a charge-coupled device, we're physically collecting those photons in the pixel, dropping the barrier, and actually moving that charge along the face of the CCD. For those of you that have an electronic engineering background, you'll remember a certain number of electrons make a coulomb. 1 coulomb flowing in 1 second is 1 ampere current. And thus, when we talk about CCD sensors that are holding 50,000 electrons in a pixel and may have 4 to 10 million pixels, there is actually a large current flowing on the surface of a CCD. Now, they, of course, try and keep the resistance low and keep that power down, but by nature, you are moving current on the face of the CCD, and that is thus developing power on the CCD face itself. For something like the Kodak 4 megapixel sensor, there's roughly half an amp flowing to read out 4 million pixels 15 times a second, and that half an amp again then makes a little over a watt on the face of the surface of the sensor. And again, besides the power, the disadvantage to that is there's a speed at which you can move those electrons around on the CCD surface. Other issues for CCD begins with blooming. Blooming is the spread of charge to adjacent pixels due to the saturation of pixels. So especially in cases where you have a bright light, in this case the sunlight in the image, and you may be using a high-speed shutter, there's a limit to how many photons can hit the surface, and the CCD can either read out through the shutter period, or it's discharging those electrons not used in the shutter period, but there's a limit to the amount of photons that can be discharged. And when they begin to oversaturate, it can spread to adjacent pixels and make blooming issues such as you see in this image. Similar to blooming, there's smearing or vertical streaking, and this is also caused by the pixels being saturated and light spilling over into the next column of pixels. So essentially what's happening here is the light is spilling over, but as I described, there's vertical and horizontal shift registers, and light is spilling into a vertical shift register. So even though that this is the hot pixel, this is the hot pixel off the glass here, these other pixels didn't have this charge, but when it rolled, because the whole image is being shifted vertically down the face, then it rolled into shift registers that were used by other pixels and continued to streak in there, and this is why you get a vertical shift, streak. And you'll notice even on the bright side of this car, there's a little bit of smearing going on here as well from the daylight. Now, a CMOS sensor then works a little bit differently. CMOS stands for complementary metal oxide semiconductor. CMOS technology actually came from the development of RAM chips. So in the early days of RAM for computers, and even nowadays, sometimes you still see erasable EEPROMs, and those EEPROMs were sensitive to UV light. So engineers could program a RAM that they wanted to use with certain instructions, load them in their computer, and if they wanted to change it, they would expose an area in the RAM to UV light, erase it, and start over. And someone early on recognized that, hey, these registers are arranged in an array on a chip, and that if this thing were looking at light, I might actually be able to create an image. So there's been deviation, of course. CMOS imagers are optimized for imaging, not storage of RAM data, and vice versa. But the technology really came from the development in the early days of the computer era. CMOS imagers are voltage-driven devices, and this is important. So a CCD, we talked about collecting the charge and rolling that charge around on the surface. In a CMOS imager, light striking the pixel creates a voltage proportional to the intensity. So the physical effect is the same. The light is still knocking an electron off in the silicon, but in the case of a CMOS imager, that electron is making a voltage in the well as opposed to a number of electrons that are being read out, which is a current in the well. The voltage is sampled directly at the pixel, digitized on the imager, and cleared for the next frame. It's never completely rolled around on here. There are issues to clear the imager. It's still dumped to ground, but essentially they're not moving the charge around in the same way. It's a voltage-driven device. Consequently, the CMOS imager, unlike a CCD imager, has a totally digital output. By the time the image is coming off of the imager itself, it is read out as a binary number, which we'll talk about, and it is a digital sample coming off the sensor. So CMOS cameras are totally digital devices, whereas a CCD camera contains a quasi-analog section, and depending on the manufacturer, may have more or less analog circuitry in it. So CMOS works by the ability to have multiple layers. It's a complementary metal oxide semiconductor, which means they can have complementary layers building devices on the sensor itself. This is called stack up as they build these layers. What has typically happened then is CMOS imagers, because of the stack up, we have a photosensitive well down in the bottom of the active area, but because it's built with layers, it's literally a photosensitive area in a well which has some depth. And because of this structure, then CMOS imagers typically have not used micro lenses. You'll notice in the latest generation of CMOS imagers that some of them actually advertise now that they have a micro lens and that they're increasing their sensitivity due to this. The micro lens, again, helps increase the quantum efficiency, which in turn helps increase the sensitivity. But these are newer developments of CMOS and coming from manufacturers who have actually made work on thin metal films to make these layers thinner. So you can see today CMOS imagers both with and without microlens, but the starting point for a CMOS is it usually does not have a microlens unless it's something designed for higher end imaging, in which the manufacturer has taken special steps to limit the depth of these layers and install a microlens. So between not having a microlens and some of the physics involved in the silicon, CMOS usually has a lower sensitivity than CCD just by the nature of this that's going on. The microlens helps catch it back up, but there's still some other physics that usually make it a little bit lower in the actual charge conversion. CMOS also, because the image is digitized on the sensor, tends to have an active amplifier either on every pixel or at least on columns or multiple columns. And this structure is then repeated throughout the sensor in order to get the active readout and not have to flow the charge around. The downfall to that, and we'll see some examples of this coming up, but the downfall to that is every A to D amplifier has a little bit of variation as well as its own random thermal effects, and that fixed variation between all these massive parallel A to D circuits and amplifiers causes a fixed pattern noise in the imager because it's not changing. The gain of this A to D circuit is always a little higher than the one next to it, and that's not changing. And despite manufacturers working to keep these uniform, they're never perfect. And so typically one of the key noise sources in a CMOS imager is fixed pattern noise in the background. However, because, again, they're not rolling the charge around, CMOS imagers tend to be more resistant to smearing or blooming than a CCD. So, voltage sampling is faster than rolling charge in a CCD. This, again, is akin to just taking your oscilloscope probe at a very high impedance and reading and checking what the voltage is instead of rolling the charge out, trying to roll it through a correlated double sampling circuit and read what the charge is or literally count the electrons in a CCD. Less flow of charge means less power. Voltage sampling versus rolling that charge around means more speed. So the main advantages of a CMOS sensor over a CCD sensor then tend to be speed and power consumption. And you can see this even in the consumer digital camera market. If you'll notice, the early digital cameras tended to be CCD. They tended to be lower pixel counts and lower quality than what we have today as the market was evolving. And in order to get sufficient quality, they typically use CCD, but that meant battery life and other things. And as these consumer manufacturers have pushed on the CMOS development, they've got sensors which are more than good enough for the consumer market, and then the advantage of the battery life, especially with flash and other things, how many pictures I can take over. And today you see almost exclusively in the consumer market that they're CMOS imagers. In the machine vision market, where we're concerned with the very high quality and often dynamic range and a lot of these other minor effects compared to a consumer camera, then you see that CCDs still have their place for quality and high dynamic range and very low sensitivity in these types of applications. But we see CMOS imagers being used more and more today because of the advantages of the architecture and because of advancements in the technology itself, making them more and more equal. But there are still trade-offs between CCDs and CMOS imagers to be considered by the user. There's no one clear answer here. The main disadvantages then, as I mentioned, CMOS tend to be sensitivity and pattern noise, or effects related to those. So among one of the other issues for CMOS imagers is also rolling shutter. And I have a diagram which will show this a little more clearly. But essentially in a CCD, as I showed, everything is done on the surface of an interline transfer CCD, which means the second substrate below that can be an entire ground plane. So CCD imager generates a electronic shutter by simply being able to take all those pixel wells and ground them to the substrate all at once. The substrate is large capacity compared to the pixel capacity. They're able to very quickly discharge a very large amount of current and make a complete charge efficient discharge of all the pixels very uniformly. In CMOS, then they have to get rid of the charge the same way, but they have to do it a little bit differently. The starting point for CMOS is then rolling shutter. This means that it's only going to expose one line, read out that line, then it exposes the next line, and then it reads out that line. So if these images were equal resolution and they both had 1,000 vertical lines, with a CCD and an electronic shutter, all 1,000 lines are exposed simultaneously, and the motion is frozen simultaneously from the top of the image to the bottom. There is no temporal time difference in the exposure from the first line to the last line. And in fact, this motorcycle is moving at over 160 miles an hour, and we can see the spokes and the holes in the calipers, and everything is perfectly frozen here. The CMOS imager, if this frame had 1,000 lines, there's 1,000 different exposures that took place in the frame time. So even if the frame time is relatively fast, let's say this was a 100 frame per second fast CMOS camera, there's still 1/100th of a second to take the frame, and within that 100th of a second, there's still literally 1,000 exposures that occurred. Now, when we look at this camera was taken out of a moving car where someone liked the scene and just took a picture out of a moving car. How many people really think that this railing was built slanting forward in the direction of the movement of the car? It, of course, was not. And, of course, this is the effect where the pixels that made the bar were read out at one time, and as the car was moving forward, then the next line was read out, then the next line, and, in fact, it tends to make everything shift in a slanted direction. The other thing I want to point out while we have this image up here is that the effects of rolling shutter are proportional to the velocity in pixels per second. And of course, the velocity in pixels per second for the pixels that are close to the moving car is much higher than the background. So you'll notice the rolling shutter effect is very high on something close to the car where there's a lot of perspective movement, and something like this rail, as compared to the island in the background, is relatively unaffected for this because it's a very wide field of view and there's very few pixels per out there it would be pixels per hundreds of feet. This is a diagram showing what I just described. So this is a CMOS issue, and essentially what's happening is this is an integration period. So it integrates for a period, and then it reads out that line. Then it comes down and integrates the next line, then it reads out that line. And this, you can see it in their timing diagram. This is how you have to build the timing diagram, and this is exactly what happens to your image distortion-wise. The only caveat is that if you can have, in a machine vision application, if you can have an entirely black background where there's no external light leakage, and you can set off a strobe, then there's a chance to freeze the motion in a rolling shutter type of scenario with a strobe. But again, you have to have a very controlled circumstance and let no light hit in other parts of the area where the line is photosensitive, but you do not want to see the integration of that light. So, coming back to our example, if we take an image of an object moving horizontally through our field of view with a CCD camera and global shutter, or a CMOS camera with global shutter, whether it's CCD and electronic shutter or CMOS that has global shutter, the object will be frozen and there will be one exposure for the entire frame. But in CMOS images with a rolling shutter, then again there are multiple exposures within the frame, and we see a displacement where the displacement is proportional to the horizontal velocity in pixels per time through the frame. And again, this is showing the same image coming back to the beginning, and we can see the effect in the bars because they are moving very fast past a car that is very close to them. And again, in the distance, you don't see it because the velocity in pixels per second is much less. When we talk about CCD and CMOS imagers, and this comes back to mostly CCDs in the days of TV interlace scanning, but there's progressive and interlace scanning methods for readout in cameras. There are some interlace CMOS imagers that were developed early on to intentionally mimic the TV interlace formats, but for the most part, interlace scanning tends to be a nature of a CCD device. So the image from the camera is formed by a sequence of pixel lines scanned and displayed in one of two different ways. For progressive scanning, it means all the lines are scanned and exposed at the same time and then read out. For interlace scanning, it means there's an exposure and then a readout of the odd number of lines, and then correspondingly there's a second exposure and readout of the even number of lines, and the odd and the even number of lines then fit together to make a complete frame. So this again comes back to, and you'll see several things come back to the early days of TV scanning here. So interlace scanning was used in normal TV systems, which were developed all the way back in the late 30s, early 40s. And what's essentially happening here is at the time the technology was developed and they wanted to broadcast it over radio frequencies, and we didn't have HD TV and satellite, At the time this technology was developed, they literally couldn't capture all the pixels, broadcast them, and recreate them. It would take too much bandwidth. So essentially the Americans came up with in the early days of TV and the NTSC systems was, we'll interlace these. Instead of having to get everything into a high bandwidth signal and read them out and then recreate it with high speed scanning on a CRT when your TV in 1940 was this big and full of large magnetic devices inside, they simply slowed the scanning rate in half and read out half the number of pixels. So your TV camera would then capture, as I described, the odd lines shown in gray here, and would capture lines 1, 3, 5, 7, 9, 11. It would capture them in common shutter and freeze them, but then it would read out only those lines. Then it would capture a second exposure shown by the black lines here of the even number lines, 2, 4, 6, and 8, and so forth through the imager, freeze them, and then read those out. And this would give your TV to scan it, time to scan in the same manner. So the TV only had to scan at half the rate and kind of paint the odd number of lines, and when it finished, it said, oh, now I can go back and paint the even lines in between. So this helped with the transmission and the creation of the image in the early days of broadcast. But it actually had one advantage to that, and that was that the fields, that though the frame rate itself was only 30 hertz, the fields are created at 60 hertz. So when I had high-speed motion, then the field nature of this at 60 fields per second let us capture the motion accurately. And because interlacing two fields at 60th of a second into a frame at a 30th of a second for watching on TV, our eyes were relatively immune to this, so our eyes could see both the motion and kind of the resolution, even though there was some blurring, and you'll see the blurring occurring. This is nice for TV and for our eyes, but in a machine vision system, we're usually capturing the image because we want to do some analysis on it, and then the kinds of blurring and effects that come from this interlace are then bad to us in a machine vision sense. So this is an example of a soccer ball that has been kicked with interlace blurring, and this is actual capture off a TV type of card. And you'll see the reason it's spiky is because of what I said. Half the lines are read out, and then the other half are red. And what you see is the leading edge lines here. You'll notice on the edge it's blurry out here. This were the lines that were captured first, and then the ball moved. Actually, I should say it this way. The trailing edge was captured first, then the ball moved forward this way, and then the leading edge was captured, and you're actually seeing the physical separation of what was a timed together frame is now separated by the difference in the exposure and the movement of that ball. So again, for our eyes, we wouldn't, at a ball that was kicked by a soccer player, we would never see the pattern on the ball anyway. We would just kind of see the ball, and we would see this movement. But if we're in a machine vision system and we're starting to capture frames and do analysis on them, this is ugly for the machine vision. If the machine vision were trying to do an object find and say, put a line around that ball and maybe test the pattern on the ball, it'd be having a hard time right now. In progressive scan, also called non-interlace scanning, one field equals one frame. This solves this. In progressive scanning, there is only one exposure. It's common to all the lines. The lines are then read out as I described, with the first pixels coming off the imager and sequentially all the way back to the top of the imager until the last pixel is read out. The benefit to this then is that the full frame is available as a result of a single shutter event. The downfall to this is it's a non-standard scanning system. So no longer does this progressive scan source plug into your TV or VCR, whereas any TV format camera would plug into any VCR or any other device. And not only is it not plug in, but it means that if I use a frame grabber or whatever I'm going to capture that non-standard device with, it has to be configured, because once I leave the TV standard format, there is no standard, at least in the analog realm, for the image that is created. We'll talk a little bit about digital standards and what's happening later, but As far as the video format of the coming off, it can be anything. If it says progressive scan, you can't tell what is happening. If it says TV interlace, you know that there's just under 500,000 pixels, that they're in NTSC scanning in the US, that there's 768 by 494 active pixels, and that they're built into 2-in-1 interlace, and we can build something. If I tell you I have a 1 megapixel progressive scan, you don't know anything more than there's 1 million pixels there, and I have to tell you that it's a 1-to-1 aspect ratio, and it's 1K by 1K, or that it might be 1200 by 800 and some odd lines. It can be anything. It's a non-standard format at that point. So again, this is just reiterating how progressive in interlace scanning, this is what comes out of the camera of progressive, and this is what the two fields of an interlace scan look like in the same scene. So if I were frame grabbing, this would be captured from a progressive scan camera, and these two fields would each be captured from a frame grabber as fields and joined back to a frame. So with interlace scanning, spatial resolution is reduced, but temporal resolution over time is improved. Twice as many full images are presented per second. With progressive scanning, sharper images are formed. With interlace, you'll see smoother motion, but we'll also notice the interline images in the image, just as I described watching TV there. I told you several things came back to the old days of TV, and this is image format is one of the things that we get a lot of questions on. And the truth is, it comes back to the old days of TV. And a lot of people are confused by the fact that optically, whether we're talking to the optics people about lenses or whether we're talking to the camera people about the optical format of the sensor in the camera, a lot of people are confused by the fact that a 1-inch sensor has no bearing to 1 inch in physical size, and a 1/2-inch sensor has no bearing to 1/2 inch in physical size. Or does it? The truth is, it comes back from the old days when there were neither CCD nor CMOS sensors. TVs were actually made in tubes, just like the tubes that used to project the TV onto your display. They used to be collected, and they had a photosensitive area in an electronic tube with a magnetic deflection yoke around it. So what happened is what became 1-inch format was literally based on the physical dimensions of a 1-inch tube, and this was how much photosensitive area fit inside the deflection yoke of a 1-inch tube in 1942. Thus, we got 1-inch format and derivatives 2/3, 1/2 inch, 1/3, and even 1/4 as they came along. And so when we say 1-inch format, all of us machine vision people, if it's a 4:3 aspect ratio, mean 12.8 millimeters by 9.3 or 16 millimeters on the diagonal. And again, a lot of users then are confused because they think 1-inch format, they're expecting 25 millimeter diagonal or 25 horizontal or something related. And in fact, again, it's just the photosensitive area that fit in that 1-inch tube. The other thing that's interesting to note here, though, BIPM, I'm not even going to try and say that, which is the metric equivalent in Europe, recommended to use metric designation. So when you see the BIPM designation, you'll note it actually matches the diagonal of the format, and like a lot of things, it makes more common sense in the metric system there. The other thing I want to talk real quick about is lens mounts, C mount and CS mount. For machine vision cameras, we do see other mounts nowadays. There are larger mounts, F mounts, M42, and some of the things coming along with the very large imagers. But the most common mount on machine vision cameras is still by far C mount, and within that, a substandard of that called CS mount. And this is a diagram showing what's happening with the lenses in a standard C mount camera. So you have a focal plane, and that focal plane is inside the camera, separated by some distance to the C-mount threads on the front of the camera to which the lens threads into. That distance for standard C-mount is 17.526 millimeters. CS mount then simply means that it is exactly 5 millimeters shorter on that back flange, and it is only 12.526 millimeters. CS mount actually stands for, or I was always told that it was security. And the reason this is important is, and the reason that it comes around with the shorter back flange is, when you want a very wide angle lens, then if we place the back of the lens closer to the focal plane, it makes it much easier to create it. So this is why you still see CS mount lenses out there, and in very wide angle applications, especially security, then they prefer this type of mount. But we also find that it causes a lot of confusion for customers, because they'll have a CS mount camera and a C mount lens, or vice versa. They'll have a CS mount lens and a C mount camera, and they're not sure what to do. Since it's only a physical difference of 5 millimeters, then you have to think of this only in a physical sense. So we can add we can take a 5 millimeter adapter ring and a C mount lens, and we can put it on a CS mount camera. The CS mount camera expected only 12.5 millimeters, too short. The lens was designed for 17, so we can add a ring and get the right distance. However, what gets people is you cannot do the reverse of this, because you cannot take a 5 millimeter adapter ring and a CS mount lens and use it on a C mount camera, because the C mount camera was designed for 17 millimeters, and you would need to remove, not add 5 millimeters to make the CS mount lens work. So unless you're taking your camera to a machine shop, you're not going to use the CS mount lens on your C mount camera. The other thing we want to mention is these distances that we give are given in free air, or what we call effective distance. This is the physical distance if it were a single lens in free air. But cameras often have glass filters in between to protect protective windows on the imager itself. Even filters for the manufacturers, color filters in color cameras, and sometimes users actually screw filters in the bottom of the C-mount threads and put between the lens and the bottom of the threads. This is okay because you can adjust back to that 17.526 ideal parameter, but that means, again, the effective distance is always 17.526. The physical distance may be longer if I put a piece of glass in there, because the glass slows down the light relative to the speed of light in air, and that causes the distance to lengthen slightly. But all the calculations would still be based on 17.526. So, in summary, a number of photons hitting a pixel during an exposure time creates a number of electrons in the pixel well, which form a charge that is converted by a capacitor into a voltage, or read down the face of the CCD, to be amplified and then digitized, resulting in a digital gray value for that pixel. CCD then is high image quality, but typically lower speed. CMOS then tends to be higher speed, but lower image quality. And again, pay attention to whether you have a global or a rolling shutter situation, and don't use rolling shutter for motion. This concludes section 1 of the presentation.